Man, my brother made this tara masala and it's so good.
This is the start of a marathon, essentially, is what we're doing right now. It's a 40K run down the Haskell line, and it all starts with this one type optional. So basically, this course, I think the whole point of this course is to basically re-implement the standard lib in Haskell. So everything has like kind of similar names to what the actual thing is in the standard lib, just given like a different name so that you can basically re-implement as if it was in the standard lib. So a quick refresher on what I'll do. Quick refresher. So a lot of what we're going to do today is just some basic pattern matching and just getting comfortable with implementing certain functions. So if we just go back and think, there's really kind of two different types that we can have. And if we kind of think about the bit, for example, so we said the bit was either true or false. So
we're not saying anything.
What's up?
We're not saying anything.
Say nothing.
Oh, you're not saying anything?
I understand that bit.
Wait, are you saying anything now?
Just a frozen screen.
No? Oh, that. I'll already share. Is that better?
That's better, yeah.
Okay, sweet. So we think kind of back to, the very simple type is the bit type, right? And we're thinking here, bit, right? Bit is a type constructor, and true and false are our value constructors. So bit, really what bit is, bit will construct types, but because bit doesn't take any arguments, right? There's no arguments there. It has no choice. It's like, give me one, that's all I can do. It's just, I'm type bit. I can't change anything, right? I can't change who I am. I'm just a bit, right? And true and false are the same thing. They create values, but they don't take arguments, so they don't really have a choice. It's a true is a true, and a false is a false is a false. There's no negotiation in that. And so if we have a function that takes a bit and say returns a bit, when we're pattern matching, we're really saying, okay, cool. Either it was constructed with true, and I can do something, or it was constructed with false. That's when it comes to a sum type, that's our options. And then the other way we could have a type is we could have some like 2D point 2D, and we could say that point 2D is, two integers in, say, some, an x or y coordinate. And in that case, again, when we think about pattern matching, well, if you think about, again, point 2D is the type constructor, and the value constructor is, so this is a bit of a weird one, right? Where you've got a type constructor called point 2D and a value constructor called point 2D. But the value constructor here on this right-hand side is basically just saying, okay, cool. To construct something of type point 2D, I have to take two integers. And if we think about, okay, now you want to implement a function that takes a point 2D and returns a point 2D, we have to think about, when it comes to pattern matching, we have to think about how could you have constructed something of point 2D? And your only choice is to use the one value constructor that we have on the right-hand side and say, well, you must have called point 2D with two integers, we'll call them x and y, and then we'll do something with that. So that's kind of the mechanism here of pattern matching. Pattern matching is nothing more than I'm going to try and like reverse the process of construction, right? When I might construct something called point 2D with 1 and 2, and pattern matching is saying, how can I reverse that process? How can I like pull it apart once it's already been constructed? It's almost it's destruction is what, when you say something like in JavaScript, like const x equals, x is 5, we call this as like this is like destruction, right? We're doing destructing here. It's kind of borrowed from the idea that you're trying to deconstruct how something was constructed originally. So how are you feeling about that? Is that?
Okay, I think for me, like I'm not familiar enough yet with the syntax to know what's going on at each of those steps that you're writing. Like that's where I'm struggling. I understood the syntax when you were talking through it last time as we went, but it hasn't stuck yet. So that's where I'm a bit stuck. But I kind of understand the philosophy at least.
That's a great place to be, Dave. You just enjoy being in that spot because that doesn't change. Yeah, so I kind of get what's going on here, but I'm not 100% sure what's going on here.
Okay. Yeah, that's how I feel. I feel like if I just went and spent some time like going through, the introduction. Like I would re-listen to what we did last time, and then I'd try some simple, I don't know, write some simple function or something. I'd be a bit closer.
Like I think, yeah, totally. I think sometimes it's just better off to just go like, all right, I'm just going to try and re-implement something really simple on my own without any, following anything to kind of work out what exactly it is I don't understand about it. But the kind of the one little step up from, so if you kind of think about, we did bit and, 0.2D, but I guess like where this course starts is with this optional type, right? An optional type is really trying to capture the idea of there being 0 or 1 of something, right? And if you think about it, we deal with this, say in maths, right? We might say, if I got a function, right, and it takes, say we got divide. We've got a function called divide, and it takes, two numbers a, b, and it's literally just a divided by b. Now, this function it's actually, if you think about what happens when b is 0, right? When I call divide with 1 and 0, it's undefined because we can't divide anything by 0. So in this case, right, we would, if you were to do this in JavaScript, you'd throw some exception saying like you can't divide by 0. And what we want to capture is the idea that this function is what they call a partial function. It's not, you can't give it any integer. For all integers, there are some integers which it just goes, hey, I gotta know, I can't deal with this value, right? And so what we want to do is we want to turn this into a function in the sense that it doesn't matter what number we give it, it should be able to give us a result back, right? It shouldn't throw an exception. It should handle that case. And we do that with the idea of an optional. The idea that, I might give you the value back or I might give you back nothing because there was no way for me to perform that computation. So, if you think about what that might look like, that I might say, well, when I call divide with, let's say, 3 and 1, that's good. We can, that's 3. But then when I call with 0, it's like, well, I don't know what to do, right? So we can wrap it here and we can say, do you know what? Instead of just returning you the value, I'm going to turn you like a wrapper that says kind of it's like a container type that says, hey, either this thing has a value in it or it doesn't. So we could say, all right, I'm going to have full of 3 here, and in this case, I'm going to have empty. So now it returns a value. It's just that when it's 0, we don't return any integer with it. It's kind of like returning a pair, and then in the case of 0 saying, you know what, there was actually nothing we could return because we couldn't perform that computation. So one of the reasons that optional is so helpful is it makes these functions, which are called partial functions, that that there are some inputs which will cause it to break, to basically allow you now to be free to call it with anything. You're not constrained. You can kind of make it a function. Go better. Why were you saying something better?
No, I didn't say anything. I was on mute.
Oh, yeah.
This is like a maybe type in other languages.
Yeah, totally.
Right?
I mean, it's maybe in Haskell is what it's called, but in this case, we're reinventing maybe.
I think I remember seeing this in Reason where it's like you do. I can't remember if it's a maybe in Reason or something else, but it's like, and then you return like a sum or something on it. It's like
yeah, that would be
right?
like, you would say like sum of 3 in this case, and then what's like the null case in None. Cool.
Yeah, none.
So that's basically, they're equivalent, just different names for the same concept. But in terms from like, why you want these things, there are a lot of times where you want to say like either the thing worked and I got a value, or like you couldn't do the thing.
Oh, hang on. So in Haskell, full is the equivalent to some.
In actual Haskell, it's like you've got just 3, or you've got what is it? Nothing. Right. So that's what it actually is in Haskell. But we're gonna like re-implement maybe. We're gonna call it optional, and we're gonna have full or empty.
Right. Okay.
So that's one of that's kind of like this motivation of it's great to have values, but sometimes we want to capture this idea of another way to look at optional is that it's a list with one element, 0 or 1 element, right? Either I have nothing inside or I have a list of 1 element. So it's like a constrained list. It's not an infinitely growing list. We can just say it's either has 2 states, either empty list or a list with 1 element. That's another way to kind of think about it intuitively. So that's what we say here. And what's a bit different here is that when we define optional, we say it's an optional of A, right? So what's this A thing? What's this A business? Like before, we just said, well, data bit is just true or false, right? We never talked about anything on the left-hand side here. But what A here is actually, A in this sense is just a type, it's an arbitrary type. It's like a generic, right? It's just like, I think, in TypeScript you have, generics and this idea of you can just have some, you don't care what it is, you're just like, it's just some type and I don't really care what it is. And so what we're saying here is that optional of A is either a full of A or an empty. There's my 2 choices. Either I'm full of A or I'm empty. Just like it's true or it's false. You can't have anything else. And so...
What's this deriving bullshit? Why do you always have to...
Yeah.
deriving
Hey, don't poo-poo on the deriving, all right? It does a lot of work for you that you don't want to do, okay? So if I didn't do deriving right, and I loaded that, oh, yeah, of course it'd say that. All right, let's go back. Where was it? Course.
Don't get us into monads already.
Hey, don't shut your eyes. Where were we? Optional. I'm just gonna get back deriving EQ. No, we can't do that. That is not a thing we can do. Why is that not letting me? Where am I? Get me out. The reason we have to use show and deriving, so show really is just nothing more than, hey, can you work out, oh, it's got into a weird state now.
That's because you're using this deriving thing. I think if you get rid of it, it'll all be fine.
Where are we? Course, come back. So you start misspeaking, you start speaking poorly of deriving and then all of a sudden things start breaking. All right, just let it be. All deriving says is that, okay, this is, I don't really want to get into this, but basically you've got this idea of a type class, right, which is like an interface that you have to implement. So you could say something like, you know what, this optional type, I wanted to implement the show interface, which just says that...
Is that just like instead like letting it know that you can do console logs on it?
Basically, it's basically just like, how do I turn into a string? And it's like, well, you know what, I could implement my own version of it. I could say, you know what, there's an instance of the show interface, if you like, and for optional.
And what's equal doing?
Equal is just going like, if I've got some optional 1 and some optional 2, I can like compare them.
What? So you don't get that shit out of the box? The language doesn't give that to you? Well, I guess the language does give it to you, but you have to then like attach it to every data type that you create.
Well, you think about it like this. In like an OO language, your comparison is usually, you're looking like, are they like referentially equivalent? Are they the same reference? Whereas here, there's no real concept of like referential equality. You're more talking about value equality. Are these two things structurally the same? And to do that, like Haskell can derive that quite easily. In this case, it just says, well, if they're both fulls and the A is the same thing, then it's the same thing. Or if they're both empties, they're the same thing. But sometimes it can't know the semantics of what an optional is, or whatever your data type is.
We have value-based reference, like we have value reference in JavaScript. We don't have to have deriving.
Well, that's only true for primitives. Right, like a number, I get two numbers and they'll compare the value. They won't compare whether they're the same pointer to the same object. But if I have a class and I instantiate a new object from a class, it'll go like, I compare the two and say, yeah, are they the same like object in terms of in memory? Or to do a comparison, you'd have to do like a deep equals and go over and check every field in that object to see if they have the same value pairwise.
Still reckon it's bullshit.
It's just one line, and you get it for free. It's like, it's like 2 for 1.
You have to know. You have to know in advance what you want, right?
In this case.
Well, every time that you declare a new type,
yeah,
you have to go like, okay, I want to maybe do a console log on it, and I want to like check for value-based. Equality, like whatever.
Well, basically, yeah. That is, but that would be also true in like other languages. Like C++, for example. You've still got to implement the operators for equality and for printing to the console. Like you still have to do the same thing. It's just that like anytime you've got a value-based system or type system, you've got to have this work of saying like, well, you just can't use the fact that the 2 pointers are the same as equality. You've got to do a bit more work to work that out. And usually what you do is by default, you'll just try and get as much as you can for free. And then if the semantics of that, or it can't work that out by itself, then you'll go in and actually like define implementation for it.
Okay, carry on.
So kind of what's the first thing you have to do, right? First thing that we'll do here is we're going to do this thing called mapOptional. So we've all seen map, right? Oh, I'm getting some weird errors. But if I say I want to map plus, actually bad example. Well, I want to map +1 over the list 1, 2, 3. Oh, what are we doing here? Couldn't get. Oh, of course. Of course I can't do that. If I jump into another tab, what happens? Can you still see that, or is it stopped? Can you see the new terminal?
No.
You only see the old terminal. Okay. Oh, that's not gonna help me. So the funny thing, because this is loading like, oh, I might be able to get away with it if I say import prelude, and then I try and map. Doesn't know what I'm talking about. Okay, cool. So just think that fmap here is map, but we know this idea of mapping some functions. So here we're saying I want to map this function +1, and maybe we'll say add1 as a function, take some number, and it just does n+1, right? So we're going to define a function called add1 that all it does is take some number n and it just adds 1 to it. Now we're going to say, cool, I want to map add1 over 1, 2, 3, the list 1, 2, 3, and it will call add1 for each element in the list. So I think we're all familiar with the idea of mapping some function over a list, certainly. But the thing is, mapping isn't unique to just a list. You can map a function over any data type, right? And that's kind of the idea here, is that what we're going to do is we're going to jump out of here, jump back into here, and we want to implement this map function for an optional type. So if I jump back into the course, optional, I don't know why that's making it hard. So you want to do the same thing where we say, I've got map optional, I give it some function, and then it's going to map the value, the function over the type maybe. So we think about how do we construct how to construct an optional. We can say either an optional is full of some value or it's empty, right? So I could say, optional 1 is full 5, which means that now we have a full value of 5. Or I could say optional 2 equals empty. And in this case, then the value is empty, right? So in here we've got a full of 5 or we've got empty. There's the kind of two values. And so if we go, add again is a function where we take a number and we add 1. If I say I want to fmap, or in this case map optional, right? This function add, and we'll call it add 1, over the optional 1, which is full 5. What we want to happen is we want to get that function and we want to apply it to the value that is within full, and then we want to return an optional, right, of full 6. So in this case, we want to return full 6. Does that
Fully 6.
Is that kind of like, does that make sense, or is that fuzzy? How do you feel about mapping a function over an optional?
Like, I haven't watched all the previous videos, so forgive me if you've already gone over this, but like, how does Haskell know that map optional is a mapping like function? What's like, is it just looking at the keyword map?
Yeah, that's a really good point.
Where is that defined?
So yeah. So basically anything to implement. So just like we can derive show and equality, there's another. So show and equality are just type classes. Like they're literally just interfaces, really. And there's another like interface or type class called functor. And functor just says I have a method called fmap. And when you try and call fmap on me, this is a function you should like go and grab and use. So it's like basically it's the fact that you've implemented a certain method which tells Haskell like, oh, here's what, if I give you an optional, here's what I'm going to go look. I'm going to look for the fmap for the optional here, and I'm going to use it in this place.
Is that done for you?
So we haven't. Sorry, you go.
Have you defined it, or have you had to define it or not?
I was saying the same thing. Like, is that automatically making the connection to your optional type above there, or are you defining that link to fmap?
So in this case, we're going to like explicitly say there's a function called mapOptional which has the same behavior as fmap, but you actually, you could also do fmap add 1 over option 1. But to do that,
hang on. You're creating like map, like line 2 map optional add 1 op 1 is actually like declaring the function name map optional.
Yeah, exactly. We're going to define a function called mapOptional that has the same semantics as if you give me a function and an optional, I'll map the function over the value and return you back an optional.
Right. So that would be the same way, like in JavaScript, you'd write function map optional returns add 1, which takes in option 1 and whatever. Like that's kind of what we're doing here.
Well, it's kind of a little bit different in the sense that we don't have, obviously you could write, a class that had the same semantics as an optional. But this is more like, I think what you're saying, like we have a function called mapOptional and we take in some function and we take in an optional and we then would return, an optional. Is that what you said?
I'm trying to work out the power. Like, I don't know, Dan,
I think I was just a little
confused.
If
it is, I feel the same way. Like, I'm trying to work
map
out.
optional had already been defined automatically somewhere, but you're just You're just writing the
Totally. No,
comment
so
of what would
that's it, just
output.
hiding down there.
Okay, so you've got it there. Yeah.
So that's what we're gonna do that, and then here it's just gonna tell us like what do we expect. So if I give you a function called +1, well, yeah, if I give you the function, it's a bit weird here, right? We're partially applying 1 to the function plus, so that we got a function that just takes one argument and returns,
good.
It +1. But
I
basically, it's like
I just hadn't seen that.
Sorry, you go.
Yeah, we hadn't defined this function, but we were referencing it. Yeah, so it's all good.
Totally, I'm with you. Okay, perfect. I mean, yeah, we can't exactly. So, sweet. So, given that, Vito, does that kind of answer kind of your query as well? This idea of like where the hell is this map function coming from?
I guess the other thing that's like a little bit opaque here is like, so we're like creating optional, right, from scratch.
From scratch, baby.
Like,
From
creating
brand
maybe
spanking
from
new.
But it would be good to see it, like what the maybe actually looks like in practice first.
Oh yeah,
so it's
okay.
like, do you know what I mean? It's like, yeah, cool, we're creating it, but I don't know how it gets used or whatever. It's like, what's the use case for a maybe?
So in Haskell, you might have, so the type is maybe, right? And it would look like literally maybe is maybe of A, just of A or nothing. But to use it, you would say, oh god, there's so many different places you would use it. But you think about it in the simple sense. What's a good example of like? I mean, yeah, okay. What about like if you had some kind of like map, right? And you had a key, and you wanted to like, see if you want to get a value from that object, right? So you had an object, and you want to get some value at some key, right? Now, there's a chance that there's nothing at that key, right? There's no value. So what do you return back? Now, in JavaScript, you return back null or undefined or something to represent like, oh, it's not here. But you don't. The thing is, there is a concept of null or undefined in Haskell in the sense that you actually encode that semantic in another type as opposed to letting it just be a value that's in every type. So when you do kind of like get on a map, you might say, okay, I'm going to return back either just of a value or nothing if it wasn't in the map. And do you know what I mean? So I think like, yeah, it'll be a lot of syntax to go like actually implement that in Haskell. But that's kind of the idea here, is that you're using it for things where it's like you give me something for a function and I can't always give you something back. There's going to be some times where I can't give you something back, and in those instances I'm going to give you nothing as opposed to just of that value.
Does that mean that like when you're defining or declaring a function, so we've got this function, like you said, it's like this map thing that maps over keys. We'll call it key mapper, the key mapper function.
Yeah, like say we had something like get, which takes like a string and it's going to return you a string. And we've got let's just make up some notation, right? We've got like a map, we've got a map here, right? And it's like, hey, you, right?
Yeah.
And we would say, okay, cool, you give me a string and I'll get you back the string that it maps to. Now, if you said...
Specifically, like get specifically looks for the key, like, hey, or something. Right?
Yeah, so like get value, right? It gets value for key if you're like really explicit.
Yeah.
So if I said get value for key, hey, it would say, sweet, I'll return just you.
Yeah.
But if I said not here, it would say nothing. I'll give you nothing back.
Great. So how does that look like if you actually create the get value for key function?
Well, it just looks like you would, look, in this case, so how it would look is that you would basically check if it's in there, and if it is in there, then you would kind of like, if you can imagine, like, you could say, all right, I take some map M, and imagine it's like an operation that's like, oh, sorry, I take, in this case, it'd be like, I'll pass the map as a value, right? So I'll be like, I take some map M and a key, and imagine there's an operation called like M in key or something, right? Then I return just, you know,
no, what is it? The value.
you know, getting the
Yeah.
value,
Yeah.
or I would turn nothing. So this might be like a function that's like contains, which returns a boolean, and I give it
Yeah.
M in the key, and then it's like, all right, cool. This is either I give you a value or I give you nothing.
I guess the thing, my question is like the maybe here is never explicitly mentioned.
Okay, that's a good.
You know
That's a really good point, right? Because maybe is a type constructor, right? So what that means that these things, just and nothing, are of type maybe. But you know, maybe in itself is never used. So it's, you know, it's not. It's the same as saying like, you know, evens is 2 or 4 or 6 or 8, and everywhere I use 2 and 4, and you know, I say like, you know, I say get key, and I say 2, or I say map and 2, right? 2 here is a value of the type evens. But you never see evens because that's what the type is. You'll only ever see maybe A in the type signature, for example, because it's a type, right? So if we said get value for key and we say string to string, well, you'll see maybe here because it's a type. But when we're talking about actual implementation, we're talking about the values.
Gotcha. Yeah, right. So if I see a just, like, because that just is like an implementation of the maybe type, right? So it's like, if I see a just somewhere, I'm like, oh, cool. Then
Exactly. If you say, sorry, you go.
Yeah. No. I get this thing wants to return a maybe. There's like it's going to return something and it might return something else.
You can think of when you say just of something as that's a value of type maybe, right? And if I say just of 5, that's of type maybe int.
Yeah.
So like just 5 is a type of maybe int, and just 6 is a type of maybe int, and just 7. And if I said just true, that's a type of maybe bool.
Yeah, gotcha.
But maybe A isn't a type, right? Because we haven't given it like the argument. Oh, brutal. Is that where we are? Cool. Can you guys see that? Yeah, so Vito made like a really good point, and this is something that took me a while to get my head around, was that maybe A isn't a type, right? There is no type called maybe A. Maybe A is a type constructor. It's like a generator, or like a better analogy would be like it's like a factory function, right? It takes some type A and returns a concrete type. It's like an abstract type, if you like, right? That you can only have maybe int's a type, maybe bool's a type, you know, maybe double's a type, but there is no type called maybe A, because you have to give it an A first before you can get a concrete type. So in Haskell, you have these kind of 2 different worlds. You have the type system, which is a language of itself, and you have kind of like the value language, where you're talking about values. And so whenever, like in type signatures, we're always talking about types. We're never talking about values, but when we talk about implementation, we're always talking about values. So there's kind of these 2 different worlds that happen, like it's higher order, like the types are in a higher order than the values underneath them. But the point here is that maybe A isn't a value, isn't a type, and just A isn't a value either. You can't have a value that's just A. It has to be just of int, or a just of 5, or a just of true. It has to have some value, otherwise it's kind of nothing yet. It's like it hasn't been born. So where were we? So we've got the just, maybe. Yeah, and exactly. So if we kind of now think, all right, you know, the maybe here, now we're talking about optional. So we're going to implement the idea of a maybe, if you like. So one thing that's quite handy is being able to map a function over over a value. Over an optional. And Damo, I'll just give you like this +1 business. Very quickly, so in Haskell you can say, for example, there's a function called plus, and that's like an actual function that you can apply arguments to, right? Or you can use the function as like a infix operator. So those two things are like equivalent.
So wrapping it in the brackets removes its special operator.
Yeah, it's kind of like, it's funny because you can have a function called add, which takes AB and just goes A plus B, and you can say add 1, 2, that makes sense. But then if you want to use it as an infix, you give it the backticks. So it's kind of like you can make functions infix operators by wrapping them in backticks. Whereas for a function that has a non-alphanumeric name, it's like the opposite. By default, it thinks it's an infix operator. And then if you want to call it like you would call add, you've got to wrap it in parentheses.
Right.
So
I'm not a big fan of weird function names anyway, so I struggle to see why anyone would name a function.
Yeah, I mean, this is kind of nice and terse, but certainly whenever, you can only really do these things when it's makes semantic sense. A lot of times where it's you have your own data type, and sometimes it's easier to give a name to the thing you're trying to do to the two types. But the weird thing here is that, say add, for example, right? Add, if I call add with 1, you'll actually return me a function that's waiting to have its next argument. So this is kind of the idea of currying, where you'll basically curry. You'll keep returning functions until you finally get your last argument, which will then you'll call the function with the arguments passed to it.
Okay.
So that's why you can do this, and that actually just returns a function that's waiting for the next arg, and then it will return 1 plus whatever you give it.
Yeah.
So you could go 2, and that would give you 3.
Mm-hmm.
So down here we're just saying, cool, I'm just going to create a function that's waiting for 1 argument. I'm going to add 1 to it, and I want to map that over empty, and it should return empty. And in this case it says I want to map this over a full, and I want to return, I want to increment the value in the full by 1 and return a full of that value. So the fun part, the part that we've all been waiting for, here it is. First function. How you feel confident? I'm feeling some hesitation. It's gonna be a rough ride, but we can do it. We just gotta stay strong.
I gotta unbox that full once I get it, right? If I use mapOptional on a full 8, and I get back full 9, what am I doing with this full 9?
Well,
I want to put 9 somewhere, not full 9.
Yeah, that's a good point. But there's in Haskell, it's less about trying to pull values out of things, and you just start combining structures that can deal with these things being wrapped. So you can actually get away. You can get most of the way that haven't to ever pull the value out.
I got a function that does another function. It's function all days. Everyone's passing shit around.
Hey, give me a function.
To put it in a database somewhere, and it can't be full 9. What's my 9 looking like?
Because the thing is, you can have a function that says, I want to take the value out of it and then write that to the database. You don't need to pull the value out explicitly. You can say, I'm going to run a function over that knows how to get the value out, call my function, and then I'm going to do something with that value.
So they treat that as an implementation detail that's left up to the programmer. If you want to get values out, and write some little pull out the value function. Otherwise, we're just carrying shit. We're just moving shit around all day. It's hot potato.
It's
Value
just
never
pass it on.
touches
Don't
the ground.
unwrap. Don't unwrap it. Just pass it on. No need to pull it out, because if you got to pull it out, you have to worry about what's the implementation details of that.
Reality is lava. Never touch lava.
Don't
Always
touch
keep
it. Leave it in there. You don't want to know what's in the box. All right, it's Pandora's box if you get it out. So if you look at mapOptional, right, it has 2 arguments, and I kind of think it's sometimes hard to read when it's like that. So we have 2 arguments. We've got a function a to b and an optional of a. So we can get a function out, and we can get some optional, right? So what are the cases? If I start to think about this, right, I'm thinking about how would I implement this, right? I want to apply this function over the value inside the optional. So what are the cases for optional? Like what could this optional actually be, right? We're talking about values here. So we can think about what are the actual values of optional. If we know that this is the implementation. What could I replace optional for? So right now I know nothing about optional, but I want to start like prying openly on a pattern match on optional and get to it.
Well, can you put a full in there, like a full 2 or some shit?
Hey, I'll take a full 2. Sounds good to me. Now, close, but what if it's a full anything else but 2?
But are we defining it now or not?
We're defining it. At this point, we're talking about defining it, yeah.
As in you want it to be full int.
Well, full int would be a type.
Yeah,
Well,
that's right. That's why I said 2. What the fuck? What do you mean?
Yeah, no, but that's like saying, what you said there's like very close, but it's a bit like me saying mapOptional 2, and then I go and do something, right? I've like named...
it's in full of A. Is that what we're meant to put?
Hey, yeah, I'm liking that. Full of A.
Right.
Or full of X, or full of Y, or full of L, anything. Just give me a name for it.
Right.
All right, and when we get... Okay, so now we've got full of A. What are we going to do? What are we going to return? We need to return a full, but what do we think we should do? We've got a function, we've got an A, and we've got a function that takes A to B, and we have to return an optional of B.
Well, couldn't you have like full B or empty, something like that?
As in like, so, I say it again, demo?
Well, can you use the optional type for the return value here instead of full?
Oh, yeah, I'm with you. Okay. Yeah, I mean, yeah, it's a good point. You kind of like, here we pattern match and we say it's full, so we know that it's a full. I think like you're kind of saying like, well, if we could just say like, if this was, some optional, I don't know what it is, but I just want to use that as the return value.
If we're defining it as full, aren't we losing the advantage of the optional data type?
Well, in this case, we're saying in the case that it's a full of A, what do we do? Like we're handling the like positive case of like, it's almost like a switch. If it's a full of A, what are we going to do? And then
it's a full of A, we return the full of B. No, is that right?
All right. Well, okay, full of B. What's B? I can tell Anthony is he's just going, there's the puzzle's there to be solved.
What's B?
What's B? How do I get a B? If I got an A and I got a function that takes A to B, how would I get this B? Because
it's the return value of full of A, no?
Well, if you think, right now if I just said, hey Haskell, run that, it would say, what the hell is this B thing? I've got no idea what this B is.
It says what the hell is anything anytime you run the Haskell compiler. It's so precious.
Well, if you think about, we've got the A out, but what does function need? Like we've got this function, what do we need to pass to the function?
You got to pass.
Oh, no.
You've got it so close.
Isn't it like, I would have thought you pass it again, like function full of function. full of, like something like that. Yeah,
All
full
right.
of B, like that. I don't know, something like that.
Wouldn't you be passing A into the function there?
Oh, Damo, music to my ears.
Oh.
Music to my ears. That's exactly right. So to get an optional of B, we need to call A, our value A, then that will yield a value of B, or not a type B, and then we can return an optional of B. That's how we get to the A to the B.
What the fuck is that syntax? Why isn't it function of full of A? Why is it full of function A?
As in, like, you want something like that.
No, like equals, like on the right-hand side,
Yeah.
it just says like function, like fn space full of A. Fn full, full A.
Well, here this says the function is going to be called with some optional, an optional of A. That's like, that would only work if mapOptional had the type optional of A and return to B, right? Because you're saying, I'm going to call this function with an optional of A. But we've got to call it with A, right? Which is what we get out of the optional.
Go back to the actual answer. What is it? It's full of function A.
Yeah, because if you think about what does that return, right? So function A will return us something of type B, and now we can construct an optional of B by using full of this type B that's returned from A.
Oh, okay, gotcha.
It's
You with
like
me?
typecasting, right? Typecasting the function return B.
As in, wait, you said, I heard typecasting.
Full would be the typecast of that function of A, right?
Yeah, it's kind of like if you think about like optional, because we've only got two values here for optional, it's either full of A or empty. Like,
Yeah.
do you know, theoretically we could say this is empty.
Yeah, totally.
That's also valid. We could say that, but it's not. It doesn't have the semantics of mapOptional. Only this does.
Because you're returning optional of B. Optional has two things it can be: full of something or empty of something.
Exactly. Yeah.
And so we need to represent that. And the way that we get to optional B is we have a look what A is doing. And A, to get to B, we need to go put a function of A. I don't know how to explain that very well, but like
that's exactly right. And that's just what they call like following the types. You just follow the types. You go like, I've got an A in a function. I need this optional B thing, and the only way I can get a B is if I call this function on A.
Does that mean we could have map optional? We could have map optional fn brackets empty of A equals empty of function A.
Okay, that's a good like segue into the next thing, right? Because at this point we haven't handled all cases. We only handled the case where there's a full, but we know an optional could be a full of A or an empty. So we have to handle the other case. So we can see here that we can't have this, right? Because there's no value constructor on the right hand side here that says you can have an empty of A. It's only empty.
Right. So it's just straight up empty.
So it's just straight up empty. And then when it's empty, what do we hang on. What do we do? If it's empty, what do we return?
You could only return empty, right?
That's there's Damon's got another idea.
The function could still have a potential data type other than empty, right?
So okay, all right. So yeah, all right. If we had to have covered full A, well, if we've got two options, full A or empty, what do you think it might be the other potential other value for it?
It really depends what that function is that you're passing in.
Well, you guaranteed.
Do we need to cater for all cases? Like, can A? So if A is an option, like A is an option of A, right? So it can be either full A or empty.
That's
saying it's empty. So then we get back optional B. Optional B is the same data type as optional A, right? So does that mean that it could be a full of function A or empty straight up?
I know you're saying the fact that A and B are different means that you could give me an optional of int and I can give you back an optional of float. Right? Because these A's and B's are different.
Have we defined, like, we've commented out on line 2, now line 3, data optional A.
Yeah.
But are we defining optional A anywhere or not? No.
Yeah, we're just up here.
Oh, we have, right.
Yeah.
Full A. Yeah, okay, it's the same. Yeah, okay. So we never defined optional B. We only define optional A.
Yeah, because A here is just like, it's arbitrary, right? Like I could say, do the exact same thing and say full of X is X. X is just a name for the argument that is of type A.
So does that mean that you could condense that whole thing down? Like, is that possible?
Into, what do you want to condense it into?
I know, because if optional A is really the same as optional B. Like,
Whoa, hey, don't you be calling those two equal. All right, so optional A.
Oh no, because optional B is a return value of the function on optional A.
Yeah, totally. Like they're the two arguments, and then I return back an optional B.
Yeah.
And you could give me a, full of 1, and I could give you back a full of true. Like, because A and B are different, but that also means that they can be the same. Like, I can make B equal to A, and now A and B are the same, but I don't necessarily have to give you back the same. The value inside can be a different type, but you still have to give me an optional. You can't get out of that. You've got to give me back an optional.
Well, fuck you, because optional B can be basically anything. So
Can be anything. Can be any B value.
So fucking put anything. Can you write the anything keyword? Put that
Anything.
there.
Well, it has to be an optional B though, right? So you want to say something like,
Or like function of anything then, or something. It's like.
But think about like optional B. You have to return optional, and you've only got 2 choices. Either it's a full of A or an empty.
I thought it could be anything.
Well, B can be anything, but you still have to have an optional.
Okay, well, it's optional anyway. I mean, like, full anything.
Well, what's anything? You want to say that? Full of A.
Oh, yeah, full of A.
But then what's A?
Well, A is an empty in this scenario, right?
Yeah, exactly.
No,
like
A isn't even defined. It's just empty.
It's like A is like a compiler go, what the hell is A? Well, I've never heard this A thing. Like X here, I can talk about X because you gave X a name, which was the value inside of the empty. But here, full of A, I don't know what that is. Like I don't know what A is. Like, you have to give me some value other than. Look, I could say full of 5, but then that would be weird if your optional is empty and I try and map over it. You just give me full of 5 back. You don't do anything else. It'd be like saying map optional over empty, and you give me full of 5. And it's like, hang on, why'd you do that? There was nothing in there. How could you give me full?
I feel like you want us to just say empty is the answer here, but my question is more around, like, what if the function you're passing has some alternate output to an empty input?
As in, like, so I pass, say, like this case here, right? mapOptional is, +1 over empty. And you're saying, like, well, what if this function wanted something else?
Yeah, what if there was just some other logic there that it was returning an error message or...
Well, this is the beautiful thing about the type system in Haskell is that when you say A to B, that there's a guarantee it can't be anything else, right? When I say that a function is, some function is string to string, it can't do anything else but take a string and return a string. It can't print to the console. It can't hit the network. It can't hit the database. It can only compute a new string and return it back. There's no other side effects it can do.
But by using optional and like, forgive me because I don't really
No,
understand.
this is good. This is good.
But by using optional with full as one of those options, isn't that covering like a whole gamut of potential? Like, how are we like, because our interface is optional, right? It's not empty. So I would understand that if the interface was, you know, empty in, empty out, but it's optional in, optional out. So
I'm with you. Okay, so you can think about like optional. So at this level, we're talking about types, right? We're talking about like there are, you know, a type. You say you can like a type's a set of values. So at this point, we're just saying, hey, look, there's some function that takes some arbitrary A to some arbitrary B. Then we take something that's of type optional A. Now, if you think about what are the values of optional A, right? They're full of A or empty. A bit like if I said add is a function that takes an integer and returns an integer. Well, at this point, we're talking about integers, not about 1, 2, 3, 4, 5. But we can think about what values can integer take. Integer could be 1 or 2 or 3 or 4. Just like when we think about optional here, optional A could be full of A or empty. They're like the values in which it could take on.
yeah, okay. I mean, so there's no way to define it in one function. You need to define it in each of those potential.
Yeah, you've got to like cover both cases. You've got to go like, because it's a sum type, so it's either it's full A or empty, you've got to handle the case where it's one thing or it's the other thing, and then do the right thing depending on, you know, each case.
Yeah.
You know, in this case, it's like an enum, and it's like, if I had a function takes an enum, I have to make sure that on, you know, in this case, I want to do something for each of the possible values of that enum, and so I'd have to like, you know, switch on for each potential value of the enum. What do I want to do in that particular case?
Yeah.
So, what I really want to say,
do we need to define, like we create mapOptional, right? With this type A into B, like this function with A and B that returns optional A, that returns optional B. Now we need to like, do we need to go and like write out all these different cases, or we're just doing this academically?
well,
Like, are we just doing, like we're just talking about all the different cases just as like theoretically, or like?
no, this covers it. This definition here is like a complete definition for
Right.
mapOptional.
On line 2, it defines it all. And we're just going through, we're just like stepping through all the possibilities that exist inside of line 1 now. Which was before line 2.
Yeah, exactly. We're thinking like this thing is broad in the sense that just like if I was gonna implement add, I wouldn't say I wouldn't say in the case where it's 0 and 0, it's 0. Or if it's 0 and 1, that's 1.
Yeah.
Do you know what I mean? You can. I mean, you could say, for some reason, if it's a full of 0, return empty. If you really wanted to say that, you could. It wouldn't make this correct, but that's, you know, that's how you would capture the fact that I want to get, when it's just 0, I want to do something special, and then any other time, if it's some arbitrary x, I'm just going to call the function on that value.
Right, gotcha. Okay, I'm sticking with that answer. A function, if the optional A is empty, then it returns empty. End of story. Just case closed.
Which is,
Put it in the compiler. Run it.
What happened then?
No, don't, because you'll probably break something.
It's not liking it. So what do we call it? We call it a optional. Okay, that's good. All right, so I think we've got this. Here we go. Will our mapOptional work? So if I say full of 1, it says, you know what? That's a full of 1. That makes sense. Full of 2 is a full of 2, right? So now we're going to define a function called add1. Takes n and just adds 1 to it. So add1 of 3 is 4. 4 is 5. What we're going to do is we're going to say, all right, we're going to call mapOptional using our function add1 over full of 2. What do we think is going to happen here? What are we going to see returned?
it's gonna return full of 3.
3, that's your vote. Anyone else want to counter that? All right, here we go. Full of 3. You love to see it. Full of 3. Now, what happens if we say full of empty?
Motherfucking empty.
Empty, right? This is no different if we said, I don't know if I said on a list, if I said add 1 to 1, 2, 3. Oh, it's not gonna. Can I? Can't map. Okay, import. I kind of just want to show there's like a connection here, right? So if I map optional, let's just call it fmap, right? If I do this, I get 2, 3, 4. I added 1 to each element. But what if I say add 1 to the empty list? Right? We all know it's empty, right? This is optional is no different here, right? If it's an empty optional, then don't do anything. Return back the empty optional. But if you have a value, call the function on that value. And so our optional is very much has this basically it's the same thing as that. If you look at map optional on add 1 on empty, we get empty, just like we got the empty list. Or if we say just of 1, which is just like our case where we had a list of 1 element. Don't use just when we're saying full. We get full of 2, just like we have a list of 2. So we can kind of see there's a correspondence here between an optional and the idea of just a list of no elements or 1 element. So I mean that was one function, but I think it was a journey on the beautiful aspect of pattern matching here. So I feel like once you got your head around this stuff, then like it's you kind of can just start like you look at the next one, it's bind, but again you're just looking at what is the definition, and then you just start thinking about the cases, right? It's really just a exercise of thinking about what cases can there be, and then what's the kind of right behavior for each of those cases.
This is the first lesson of the course?
This is the first one.
Fuck me.
I think it's a little bit like a little mountain, right? At the start, we're all a bit slow, there's a lot of stuff to get our head around. And then towards the end, it'll be like, eyes closed, implementing pattern matching. Eyes closed, bang, next one, next one, next one. Like at the checkout, you're at the Audi checkout. You'll just be going, give me the next function to implement, next one, next one, next one.
The Audi checkout. All right.
So I'll leave it.
Cameron, very good, thank you.
Hey Cam.
Yeah.
That was definitely like, that was first year maths. Like when I did maths in high school, I had a really bad teacher called Mr. Tusaho, and we never finished the syllabus. We only got halfway through by the end of the year 12. So like, I don't know how I passed it at all. Then I got to Australia where the standard is like 2 years ahead of what South Africa's standard is anyway. And I failed maths like 4 times. So I feel like I'm back in those lectures failing again. What's the best way for me to like have another second run up back to where we started today? Like, should I go and play with the little tutorial to get the syntax, the Haskell syntax, sort of my head around that, and then drop into this exercise, or like?
That's what I would do. Like in that case, if I would just try to implement like if you can do the bit data class, if you can implement data bit equals true or false, and then go and implement like or and and not and those logical operators. If you can do that, then you that's like a very good like entry point into like how do you define a type, how do you then define functions? How do you pattern match? And that's kind of where I would start. Like, just could you go through and like,
and is there, I mean, is there like reference? Like, I've got no problem reading the manual. It's just that I'm slower. So, is there?
Okay, yeah, I'm with you. There's a really good book called Learn You. I think it's like Learn You Some Haskell or something like that. That's pretty good at like explaining how these things work. So I'll just shoot you the link for that. And that
Okay, that'd be good.
has a bunch of things that just like...
I can watch the other video, but it's just like, it's a little bit fast for me. So anyway, I don't know if I'll have time in the week to keep up as you guys go, but if I don't, I might just drop out. And
hey, we're not. There's no dropouts in this
it's just it's like the amount of time that it takes me. You know, it might take me like 3 hours a week to stay up to speed that you guys can do in the 1 hour, and I'm also trying to learn like other stuff every morning.
No, totally.
Well, so.
I get that. Yeah, this is not the only thing you're doing at the moment. So,
but I'd like to try. So I'd like to like at least attempt.
I honestly think it's probably just there's only a few things that like you need to like fundamentally get your head around, and then that will like unblock a lot of what's still confusing.
Yeah. Cool.
So yeah, we can work that out.
Okay, man. Thanks. It's I'd like if I can keep up, within these hours per week, that would be amazing. So yeah,
mate, for sure. If I can have some understanding what's going on, you're gonna have no problem. Trust me.
I'm sure. Okay. Thanks,
you
dude.
can be on Slack too if you have any questions. I don't mind answering them.
Oh,
yeah.
Thanks, Andy. That's
Bye,
awesome.
Anthony.
Okay, cool.
Thanks, guys. Thanks, Cam.
Thank you.
Well, thanks for coming.
Definitely redo this lesson, like 100%.
We can
is this one going up on YouTube?
Huh?
Is this one going to be on YouTube?
Yeah, I mean, we can always pull it down if we decide later that it's too chunky.
Just that I can step back, because I know the points where I know the point is where I lost.
You lost.
I lost it, so I'd like to go back there and see if I can.
I can chuck it up on.
Thanks, man.
All right, guys. Thank you very much.
Everyone. Love it. Okay, ciao. Bye.
See ya.